Hello everyone. Can no. Alright, we're just gonna get started in a couple of minutes, so yeah, just to let some other people come online. Alrighty. So hello everyone, my name is Kabir and I'll be running the second part of the D seminar. Now, just to forward in what we're going to be covering today, it's mainly going to be centered around these three overarching ideas. Now, the purpose of this seminar is mainly to address all the exam relevant parts. Looking over the slides, there's obviously going to be some elements that are probably not going to be assessed given how difficult or how out there they are. So whenever you're going over these slides, these are the main things that can be tested in the final exam. The other thing to note is that when we start off doing initial boundary value problems, while it does say that it is mainly focused on MATH2121, the 2121 students can also find some, will also need to pay attention to some of the parts in it, because it does draw on some ideas that Anna covers in her lectures for 2121. So, without further ado, let's get through it. Wait, hold up, let me just check if I'm recording. Sorry, I don't think I started recording. Oh, okay. No, never mind. Apparently it auto records. Okay. So, alrighty. So, initial boundary value problems in 1D. So, for the most part, like, I'll let you guys know whenever MATH2121 students need to pay attention, and whenever 2221 students, whenever their information is relevant. Okay, so for now, just let's everyone focus on these. So the first thing that we go through is the concept of inner products and norms. Inner products are basically ways of measuring sizes over, this time we're defined over continuous intervals. In terms of the linear algebra aspect, we typically understand inner products over finite dimensional spaces. Sorry, over discrete spaces in a way. Sorry. Inner products in these kinds of cases will be defined as an integral, where we're integrating over a specific interval, and we are multiplying two functions pointwise and integrating over that interval. And norms are defined in a similar way to how we have the inner product, the analogous statement being the dot product. The norm is defined in a very similar way, where we take the inner product with respect to itself and then take the square root. In a similar way, when we have the dot product, we take a vector times dot producted with itself and take the square root. So norms and inner products will form the centerpieces for what we're about to see. It's very unlikely to make some mistakes in terms of these definitions, and you'll just ensure that the most common mistake that you will probably encounter is tricking yourself into thinking that f comma f is, the inner product of f and f is the norm. It's the square root of the inner product of f and f. And that is something that you'll need to take care of in an exam. That's the most common silly mistake. A couple of quick examples are basically if we take the inner product of the sine x and cosine function over the interval 0 to pi, we end up with the integral 0 to pi sine x cos x, which we can use a double angle trick, and that amounts to 0. But the norm itself will amount to the square root of pi on 2, remembering that we have to take the square root at the end of computing the integral 0 to pi of sine squared x with respect to x. If you want, you can always kind of break it down into some simpler steps. So first you compute the inner product of f and f, and then actually decide to take the norm. But at this point in time, it should be fairly second nature to remember that to get the norm, you have to take the square root. Okay, an important result that comes from this is, look, you're not going to particularly get any questions on the Cauchy-Schwarz inequality, but what the Cauchy-Schwarz inequality does is it allows you to create a relationship between the inner product and the norms of the function you're taking the inner product with respect to. So all it says is that when you have the inner product of two functions, my apologies, I'll fix up this notation. I'll get to what this notation means later. The inner product of two functions, when you square it, will always be less than or equal to the product of the square of the norms. Alternatively, you can take the square root of both sides, in which case you directly have the inner product of f and g is less than or equal to the norm of f multiplied by the norm of g. Okay. Now what we can do from the idea of inner products, we take a slight digression in terms of the idea of adjoint operators. This is primarily for the 2221 students. 2121 don't appear to cover this at all. So yeah. Okay. So with the adjoint operators, the formal adjoint is basically derived by computing some alternative forms of expressions. So we start off with a linear operator, a2 u double dash plus a1 u dash plus a0 u. And instead what we're doing is we kind of just place brackets around a2u, a1u, and a0u. Okay, so when we have, so that's basically what the formal adjoint is. It might be a little tricky to remember it, but basically just insert brackets over here whenever you're computing the formal adjoint. An important property about the adjoint is that if you take the adjoint of the adjoint, you'll end up with the original thing itself. Okay, so now onto going through a specific example. The first thing that we always do is we start by labeling each one of the coefficients. So we start off with a2 equals x, a1 equals e to the power of x, and a0 equals x squared plus 1. Then we just plug it into the definition of the formal adjoint, and we keep expanding out until we get to not necessarily simpler expression, but we get to another expression that instead computes it. Sorry about the extra noise. We compute it in terms of v. The reason we don't use u is we'll come to that idea later, because it will be important, particularly when we are computing inner products over here. Okay, so hopefully so far we're all clear on this. Okay, so in terms of like actual exam relevance of this won't play too much of a role, like in terms of computing directly what the adjoint of a formal what the formal adjoint of an operator is, that's relatively insignificant. We don't really care about that. But the property about, using the idea of adjoints will be really important when we come to more, I guess, fancy in a way theorems. So yeah, okay. Moving on to the Lagrange identity. The Lagrange identity basically says if we take the inner product of the linear operator times u with another function, we don't really care what that function is for now, but if we take the inner product of these two functions, we can in fact replace it with u times the formal adjoint operator of v plus an extra little term called the bilinear concomitant. This is really, I guess, annoying to remember, but memorize it if you have to. It's unlikely that you'll actually need this statement. So basically, the proof of this is kind of like a little long-winded, but you can brute force it out by computing what the formal adjoint is, and then writing this as an integral, and also writing this as a, I guess, and then writing this guy as an integral as well, and taking the difference of the two to show that the bilinear concomitant can be achieved. It is a very long proof, which is why we haven't discussed it, and you most definitely won't need to prove the Lagrange identity. You can just kind of quote it. Okay, so the good thing is that formal adjoints are probably not going to be assessed. But the more important thing arising from formal adjoints is the idea of an operator being formally self-adjoint. And this one's kind of like self-explanatory, where the operator itself is equal to its adjoint. And an important thing regarding this linear operator being a self-adjoint operator is that it can always be written in this form. For some expression p and q, we can always transform part of a linear operator into formally self-adjoint form. And in order to be able to do that, what we do is we use an integrating factor. So from the earlier part of DEs, when we were learning how to solve these differential equations, we were essentially expressing the left-hand side of a degree 1 of a first order differential equation in terms of this, so that we can convert it into a form that's more easily solvable. And using this integrating factor, we can arrive at this portion of the equation, and then the QU is just an extra thing that arises from using the U component from the operator L, and then if at all anything extra is needed, we can take care of that. Okay, so let's suppose that we wanted to write the following differential equation in formally self-adjoint form. So we begin by writing out the left-hand side of the equation. We don't need to really worry too much about that. And what we can do after that is make it monic. So by dividing through by x, we end up with u double dash plus u dash minus 2 over x of u equals f over x. Now after that, we realize that the integrating factor is going to be the integral of 1, which is a coefficient of u dash, e to the power of integral 1 with respect to x, which gets you e to the power of x, and we multiply the entire expression by e to the power of x. So this portion now can be expressed as e to the power of x u dash, or taken the derivative of, and then we're left with our expression for q, and we're left with our expression for the new right hand side. So our new expression overall, when we want to convert it into the specific form, remembering that we have a negative at the front, that's going to be the really important part. Again, another really, I guess, opportune moment for a silly mistake, so please make sure that you remember the negative sign. So we multiply this entire equation by -1, so that we get p is equal to negative e to the power of x. We end up with q equals 2e to the power of x all over x, and g equals negative e to the x times f all over x. Okay, so unfortunately the way most of these go will end up being very, I guess, methodical and repetitive, but it's all worth it at the end of it. Okay, so when we have formally self-adjoint operators, what ends up happening is we can convert this guy into, we can convert the L star into an L. So when we go back to the Lagrange identity, we had this. So the L star ended up converting into L, and we took the difference of the two. So now we have the inner product of LU and V minus the inner product of U and LV. So all we're really left with is the bilinear concomitant on the right hand side. Now what ends up happening as a result of that is we can convert this guy by rearranging the terms, I suppose, into this equation, which looks kind of messy, but with each one of the coefficients going on. But basically this B1 of U is a representative for one of the first boundary conditions, and this B2 of U is a representative for the other boundary condition at B. And each one of these are essentially some extra constants that you need to develop in that arise from the bilinear concomitant. Because when we have this over here, you can see that we end up with U dash at B times A2 at B times V at B. So that U dash at B plays, I guess, some kind of role involved. And over here we have the U of B, and over here again we have U of B. Then again we have A2 of A, A2 of B, V of B, and so on. So what we're essentially doing is we are condensing the bilinear concomitant into these simpler expressions. So it's just basically a rearrangement of terms. I'm not sure if he's going to include this on the formula sheet, but what you should observe is that a lot of the time you're going to end up with a really neat expression for V, in which expressions will simplify out to something really, really simple. Well, not necessarily simple, but easier to look at. It won't be extremely complicated. Okay. So, with this idea from the Lagrange identity, we can come up with a way of identifying uniqueness. Again, this is most definitely for MATH2121, and it's relatively likely that a question on the Fredholm alternative will come up. 2121, this one is most definitely not going to be assessed. So you guys don't need to worry about this slide. Okay, so the Fredholm alternative is basically a way of defining uniqueness. One thing that we can get from the previous part is that what we're doing is we want to solve for U, and V will be constructed in a way so that it is a solution to the homogeneous equation, or homogeneous equation, so that this guy ends up being 0. Now what ends up happening as a result is that we are left with the inner product of LU and V is equal to just whatever we got from the bilinear concomitant. And if we have an inhomogeneous system as we've defined over here, LU equals F, then what that essentially means is that this guy ends up being F, and the inner product of F with respect to a homogeneous solution equals something. Now, what ends up happening is that if at all the we have a homogeneous solution of, we have f is identical to 0, and each one of these boundary conditions is 0, all that means is that the only solution that you can get to the only solution to the homogeneous version of this problem is going to be the trivial solution, because the boundary conditions are 0 and L of u is going to be 0 everywhere in between. So that means that the only solution to the homogeneous version of this problem is the trivial solution, and that implies that to the inhomogeneous form, i.e. when we have LU equals f with alpha 1 and alpha 2, the only solution that you can get is a unique solution. We don't really care about whether or not it's trivial or it's non-trivial, but it's just going to be a unique solution to the inhomogeneous version, and hence the entire problem, right? We're just borrowing the idea that every solution can be expressed as a homogeneous component plus an inhomogeneous component. So whenever we have this system having a trivial homogeneous solution, the only thing you can get is the unique inhomogeneous solution. And otherwise, well, the only other case is the fact that if we have a non-trivial homogeneous solution, in other words, this V actually does contribute something, then the only thing we can really be left with is an extra condition that we can only have a solution if the inner product of f and v matches exactly what we get from the bilinear concomitant. Now, the idea being that we get the alpha i's, the alpha 1 and alpha 2 from the boundary conditions, from the boundary condition on u, and then we have this extra I of v, which is arising from PA VA over B11, and then PA V dash A over B10. So the Fredholm alternative is basically just a way of identifying whether or not a solution is unique or not, and whether or not it exists. So if the trivial solution, if the only homogeneous solution is a trivial solution, then there will always be a unique solution to the entire problem. Or if the trivial solution is no longer unique, so i.e. we have this V coming into play, then we can only have a solution, if this is true, for each one of your homogeneous solutions. Because sometimes you can have V being like sine x and cos x. So if this is applicable so if this condition applies for both V equals sine x and cos x, then you will end up with a solution. It is not going to be unique though, because the homogeneous solution constantly has those undetermined coefficients. So provided that the initial conditions for V for the homogeneous component are provided, like i.e. you're given some extra points, that's the only way you can actually arrive at a specific solution. Okay, so a quick little example on this is, let's suppose that we have L of u equals u double dash plus u, which equals f, and we're given these as our initial conditions. Now, it's already known that if we have it's already known that the homogeneous solution to this equation is a sine x. There's also the b cos x, but the reason it disappears is because of the initial conditions. So if at all we have u of 0 is 0 and u of pi is 0, then that means that the cos x can't contribute any component. The only component that can actually be contributed from is going to be the a. So, but however, because it is 0, we can't really determine what a is, so we kind of just leave it there as the extra coefficient. Okay, so once we apply the Fredholm alternative, we can only have a solution if the inner product matches what we expect from the bilinear concomitant. And if we plug in the values from the bilinear concomitant into this equation, what we end up with is a alpha 1 plus a alpha 2. And from the inner product itself, this is the expression that we end up with, the a times the integral from 0 to pi of f of x times sine x. So in other words, you can only get a solution if, after dividing by a, you have this as your final expression. In this case, because we have b1, so u dash, the coefficient for u dash of 0 is going to be 0. So in other words, this guy is going to be 0, and this guy is also going to be 0, so that's where our boundary conditions come from. b1 of u is equal to just that bit, and b2 of u is just equal to that bit. And then we can plug it in, and we have our required solutions. Alrighty, and again, this guy just ends up being 0, and this guy again ends up being 0 for when we are taking R1 of V and R2 of V. Usually it's a lot easier to just go back to the actual form for this guy over here. That's a matter of preference, I suppose. It won't really matter too much which way you do it. You'll always end up with the same, I guess, end result. Alrighty, so 2121 students, you can return back to the slides. Now we move on to the idea for generalized Fourier series. Sorry. Generalized Fourier series is admittedly has its moments of going really, I guess, out of the depth, but the idea for generalized Fourier series is that they all ultimately work in very similar ways. So the first one that we generally tend to cover, because it's the most obvious, is the normal Fourier series. And the Fourier polynomial is basically just a summation of a bunch of trigonometric terms, along with an extra constant. So let's suppose that we have a 2L periodic Fourier polynomial, so that essentially we are considering chunks of length 2L, and then it repeats itself. What we can end up doing is we can express these partial sums of associated with a function in terms of a constant plus a sum of causes and sines. Now we divide by L because we have a period 2L function, and the period of a linear combination of these is going to be 2L. And we're adding up a whole bunch of these trigonometric terms to closely match f. These such coefficients can be determined using a whole bunch of integrals, and we can immediately see the relationship with the idea of the inner product. So over here we're taking the inner product of f with 1, over here f with cos of k pi x on L, and over here with sine of k pi x over L, to determine each one of the coefficients. Now, depending on how you write the function, you can have either a0 over 2 or just the a0 bit, and that depends on just purely how you write the integral. Alrighty, so okay, so let's suppose that we have an even function. Then what one can conclude is that we can construct the entire function in terms of a constant, and then in terms of a whole bunch of cosine, I guess, inner products, with each one of your bk's being equal to 0. Now the reason for that is that when we take the inner product of an even function and an odd function, we end up with another odd function, and since we're integrating from negative L to L, the integral of that odd function will be 0. Similarly, with an odd function, what we can deduce is that we will only get our sine coefficients, because, well, when you have the inner product of an odd function with an odd function, you end up with an even function, and then you integrate from negative L to L to get the actual coefficient. Now the way this simplification works in each one of these cases is that we're using the property of even and odd functions that we can multiply by 2, and then we can reduce the interval by length half. Alrighty, so when we want to compute a Fourier series, essentially what that means is that we're taking a limit of all these partial sums until we get the entire infinite sum that we can describe a function by. So over here, let's suppose that we have a function f of x is equal to x over the interval -1 to 1, and note the discontinuity, which means that its left-hand limit is, well, it exists, but it's not continuous at that point, and then it kind of just like copies itself every 2 units, which is what this means. We repeat that graph of x from -1 to 1 every 2 units. Alrighty, so we know first up that the function is odd, which means that all we really need to do is compute the integral of x sine k pi x over L, where L is equal to 1. Because we're not integrating from -1 to 1, which is why we end up using, well, you can integrate from 0 to 1, whatever makes you feel comfortable. As long as you remember the fact that you're integrating, that you got to remember this fact that if the period is 2L, then you have to divide by L. So that's why over here we are integrating x sine k pi x, not sine k pi x on 2. Again, opportune moment for, well, not opportune, like another moment where you can make a silly mistake. So, when you have the integral of 0 to 1 x sine k pi x, you can use integration by parts and end up with this formula. And then just remember the 2 at the front because we've reduced the interval from 0 to 1. Alternatively, you could integrate 1 over L, which in this case 1, from -1 to 1, x sine k pi x on L, and you'll end up with the exact same answer. Alrighty. Now, each one of the other coefficients is going to be 0 because we were considering an odd function. So, all we're left with is all this sine k pi x's with coefficients determined by these. And the way we get -1 to the power of k plus 1 is because this guy ends up being 0 for every value of k, for every integer, positive integer k. And over here, we end up with -1 to the power of k. With the extra negative sign, it becomes -1 to the k plus 1. Alrighty. So, one thing about Fourier series is that what could potentially happen, well, you are able to create these Fourier series, but provided that they're existent over an entire interval. What I mean by that is it doesn't randomly blow up somewhere in the middle. So what we can do is instead, for a lot of the time you're not going to be considering obviously Fourier series for those, but what we can do is that whenever we have a jump discontinuity, we can try and create Fourier series describing those. So let's suppose that we have a right-hand limit of the function and a left-hand limit of the function. Then what we can deduce is that as we keep on building up the Fourier series for the function over the interval, then that Fourier representation will go in the midpoint, or like I guess halfway between the left-hand and the right-hand limit. So that I suppose that even if you do have a continuous function at x equals a, since the left-hand and right-hand limit of f will be equal, what will happen is you'll just end up with f of a Anyway, so this can be generalized, but for now we just consider jump discontinuities, in which we have a function that if it approaches, let's say, over here as we are coming from the left, and it approaches over here as we're coming from the right, then the Fourier representation will pass through the middle and then start matching the graph everywhere thereafter. So it's kind of like just average every time you have jump discontinuity. Of course, this does imply that you do need the one-sided derivatives to exist, which is one of the key requirements, that if at all it does blow up, then what ends up happening is that it goes too far up and there's no way that the limit of f exists, in a way. If at all we have a situation in which we have like a vertical tangent, then again that does cause some problems, but they're a little bit more in depth to explain. So you can only construct the Fourier series for now, whenever you're dealing with jump discontinuities between two finally valued points. Okay, so in terms of this one, let's suppose that we have the following example. This one is similar to the one that we had earlier, except this time over -1 to 1. So using that previous example, we had, sorry guys, I'll just be right back. Sorry about that. So going back to the previous example, when we were dealing with y equals x from -1 to 1, what essentially happens is that you get these kind of, I guess, diagonal slanted lines repeated. But in the previous example, we noted that we included the point 1, but we excluded the point -1. So when we construct the Fourier series, we will essentially get something like this. We'll get waves closely enough matching this line, or these lines, but instead of hitting the point 1, it will kind of like quickly tail away and hit the x-intercept at -1, and then proceed to go back down immediately to the line over here, and then closely match it up all the way again, and then it will jump back down and then keep on matching it all over again. So if you repeat it enough, what will happen is you'll end up with these straight lines, much like what we had in the previous case, except it won't ever hit -1, or 1, or 2, and so on. Sorry, 3, 1, and so on. Okay, so now what we can do is we can kind of expand this idea, and when beginning from an interval 0 to L, we can expand it to considering an interval -L to L. And one way we can do this is by considering an odd and an even extension. So an odd extension basically means you're forcing the function to be odd so that it takes on this kind of form, that it maintains its odd symmetry. We begin with the function on the right hand side, then we force it to be negative of f negative x over this entire interval. So essentially we just rotate the image by 180 degrees and then copy that graph. And with your even extension, all you're doing is you're flipping it about the line x equals 0. And in this way we can kind of create these periodic functions using these half-range expansions. Okay, so and these are kind of classic examples. Again, 2-1-2-1, you cover this, so it's probably going to be really important for you. Okay. Right, so let's suppose that we wanted to find the Fourier cosine series of f, where f of x is equal to x. Now, when we are considering the Fourier cosine series, we understand that we create an even function because we're considering a sum of cosines. So, what we do is we have g of x is equal to x for all your values between 0 and 1, and then you have negative x for all your values between -1 and 1. I apologize for the typo. I will fix it up when I update the slides. When we have a -1 to 1, so now we have a function g of x, an even function g of x between -1 and 1. We can, I guess, understand the fact that it's just basically the absolute value function, but that's just a coincidence in this case. But a lot of the time you will end up needing to use a trick similar to this. Okay, now, using this, what we end up with is, to find the coefficients, we just use integration by parts once again, and the formulas that we've defined above. So that we get 2 times the integral 0 to 1, absolute value x, cos k pi x. And using IBP, because we know that absolute value x is just equal to x over that interval, 0 to 1, we just have to integrate x cos k pi x. And similar to what we had before when finding this sine function version, we end up with -4 over k squared pi squared when k is odd, and 0 when k is even. And that's primarily just due to the fact that, due to the behavior of cos about the line x equals a half, because it's going to be 0 at half, and cos is has odd symmetry about x equals a half. Hence why we end up with this kind of alternating pattern. Alright. So, let's suppose that, and in terms of finding the constant, that's just going to be 1 in this scenario. Again, just by a similar idea that we integrate 0 to 1 of x. So that allows our Fourier series expansion to be equal to half minus 4 over pi squared, summing all over the odd terms, because k was odd whenever we had, when k was odd, we had non-zero coefficients. Okay, you can actually graph these and see what you get. Alright, so incidentally, it doesn't look like this is true, but it actually is. If you plug in x equals 0, you end up with 1 for all your odd terms. So you have the sum over all the odd terms, 1 over k squared. And that one simplifies out to be pi squared over 8. And then that's where half minus half comes from, and that's where your function is 0. So it actually does pass through the point 0. Alright, so now we introduce the extra notation, which is where the Cauchy-Schwarz definition came from. This extra notation is when we take the inner product with respect to weights. So that when we take the inner product of f and g with respect to w, we have the following definition. but we have to add in the extra requirement that w of x is greater than 0 over the open interval, and that's just to maintain some properties about the inner product. And that includes the norm that it induces, which is exactly the same definition. The norm of f being the integral a to b of wx, f of x squared. So in order to preserve that property, we have w of x is greater than 0 over this open interval. Now, in a similar way to when we had two vectors are orthogonal whenever their dot product is 0, two functions are orthogonal if their inner product is equal to 0 with respect to that particular weight. We don't really care too much about the interval because it's going to be kind of obvious, but that's basically what we're going to be considering in terms of orthogonality. Okay. So, we can create these, I guess, sets of orthogonal functions where we are essentially considering a set of functions, and when we take the inner product with respect to a particular weight, if the two functions are not identical, then their inner product is 0, and that's basically what we're calling an orthogonal set. Now, the extra requirement is that when you actually take the norm of the function, you end up with a non-zero number. Otherwise, if it's 0, you'll just end up with the trivial function, and it's kind of useless having an infinite number of trivial functions because that doesn't really tell you anything. So we add in the extra, I guess, we omit the extra idea that the norm of a function with respect to our weight is 0, because we're hereby assuming that it's not going to be 0. The norm won't be 0. So let's suppose that we have a sequence of functions, sine pi x over a, sine 2 pi x on a, sine 3 pi x on a, and so on. What we want to do is show that they are orthogonal on a set on the interval 0 to a with respect to this following weight. And when we want to prove orthogonality, all we need to do is just brute force compute the integral. So the integral from 0 to a of sine nx m pi x on a, sine m pi x on a, is equal to the following, where we are assuming that n is not equal to m. If n was equal to m, we would end up with 1 over here, and the integral would just end up being a. Yeah, so that the integral over here would just end up being a, and then we would have to subtract cos 2n pi x all over a. Again, the point is that you would end up with a non-zero number. But if n was not equal to m, then over here, over the interval 0 to a, you end up with 0, and over here, over the interval 0 to a, you again end up with 0. So the difference of the two numbers would just be 0. Okay. So going back to the idea of norm, again it's defined in exactly the same way. Please make sure you remember the square root. Okay. So if at all we wanted to find if we wanted to find the norm of a particular function, because we are considering with the weight to respect, we're considering a weight of 1, all we have to do is just normally square the function and integrate from 0 to a, followed by finding the square root. And upon simplification, we find that it's just going to be square root of a over 2. Okay. Now, what we can do from here is we can create this really cool idea of a generalized Fourier series. And generalized Fourier series have the charm in that, well, we'll get to why exactly they're super duper important. So with your generalized Fourier series, all you're doing is, instead of considering the set of trigonometric polynomials, which is what we're so used to and accustomed to, we create an analogy with different kinds of functions. So common ones are called your next most common one is called the Bessel function. Then you also got the Lagrange polynomials, Chebyshev polynomials, and so on. But they all have this idea that if you take an infinite, like if you consider each one of those, they end up creating these orthogonal sets with respect to particular weights. And what ends up happening is that you can express a function in terms of the sum of these as a linear combination of these generalized Fourier terms. And each one of your coefficients is determined by these particular inner products. Now this one, in order to prove this one is kind of like a little bit out there. We don't need to worry about the proof of why exactly this works, but we kind of just like go over the results that explain why this work. The proof for why these work is covered in 3611, so you'll find some really cool analogies that you can develop with ideas of completeness, which we'll get to. So with your generalized Fourier series, the point is that you can construct a function f in terms of each one of its coefficients, and each one of your CNs is given by inner products with respect to weights divided by the norm of the function squared. We will get to why exactly this works, but basically this one is identical to the idea of least squares regression. So if you're doing 2501 and 2601, this will be, I guess, familiar in that we are computing the dot product of two vectors divided by the square of the norm of the vector. And that's basically your least squares definition when you're projecting onto a particular space. Okay, so with regards to this next slide, we don't really need to worry about it too much for the 2121 students, but for the 2221 students, we say that a particular set is called complete if no non-trivial function can be written as a linear, in which there is no non-trivial function that is orthogonal to every single function in your set S. In other words, like if you're just computing your inner product with respect to each one of your functions in the set, you'll always end up with 0. You'll always end up with such that if each one of your inner products is equal to 0, then the function itself must be the trivial function. I suppose that this is kind of identical to being that the function is, in a way, exists in the span of your orthogonal set. So every single function in L2 is expressible as a linear combination of stuff in S. Okay, so you probably won't need to know anything about these, but you may or may not need to quote completeness. Very rarely does it ask you to actually quote it, but, or actually no. Yeah, I think there have been a couple of past exam questions in which you are required to quote completeness and what exactly it means. So it's useful to know what exactly completeness means in terms of this definition. I suppose there are equivalent definitions, but this is like the real definition. Like the rest are just kind of results that arise from the definition of completeness. So this is the definition, and then from there comes every single result regarding completeness and how generalized Fourier series work. Okay. The next one is for everyone. So we resume with explaining every single idea to everyone. Parseval's identity is basically a way where we can compute the norm of a function depending entirely upon its Fourier representation, or generalized Fourier representation. So we have f being expressed as a series of coefficients. AK is a coefficient that is determined from the inner product of f with respect to phi k. And then what ends up happening is that the inner product of f with respect to itself is equal to the sum of each one of these coefficients multiplied by its norm, by the norm of the associated function. Now, due to completeness, the converse also holds in terms of for the MATH2121 students, and that just arises if we assume that if parcel-wise identity holds for every single function in L2, then that means that the orthogonal set has to be complete. Alrighty. So, okay. So a classic example is just, I guess if you're fancy enough, it's called zeta of 4, but more relevantly, parcel-wise identity can be used to compute zeta 4 using the function f of x equals x squared. And basically, you already recognize that the function is even over this interval, so what one may do is entirely neglect the sign component of the series because sign is odd. And so all we're left with is a0 of f, which is given by the following integral, based on the definition that we've constructed above. Either this or 1 over pi, integral negative pi to pi of x squared, which equals 2 pi squared on 3. Now, ak of f is equal to each of the following integrals, given, and so what you can do is the pi disappears because on the denominator we have L equals pi, so that now x squared cos kx will just end up equaling this function. Now what ends up happening is that we still need to compute the norms of your cosine functions, so that integral, so that the weight of 1 is obviously just equal to 2 times the integral 0 to 1 of 1, which gets you 2 pi, and cos k pi with respect to 1, the norm of that squared is given by the following integral, in which you get pi. Now, plugging that and the norm of f with respect to the weight 1, you end up with, you just plug it into parcel-wise identity, which I guess isn't too bad to remember. The more important part is just remembering that you've got to square everything, but making sure that you don't put the squares on the outside instead of the inside. Plugging everything in, we end up with the following expression, remembering the divided by 2, depending on which definition you've used. And what ends up happening is you get the following expression. And once you finish rearranging the entire equation, you get the sum of each one of your powers of 4, reciprocated powers of 4, will get you pi to the 4 on 19. There are, of course, other ways of doing this, but parcel-wise identity gets you there kind of the quickest. Okay. Yeah, so far we're going on time. So, now we move on to the theory of Sturm-Liouville equations. This one is mainly a 2221 idea, so the 2121 students don't need to know about this. Okay. So, the Sturm-Liouville equations basically allow us to construct a differential equation similar to what we had from the self-adjoint form. So, a Sturm-Liouville equation is basically something of this form, which looks remarkably similar to what we had from this self-adjoint form. in that we have the similar idea of pu dash, all differentiated, minus q of u, in which case that's just the negative of what we had from the self-adjoint operator. And then we have this extra component, lambda r, which kind of creates a new form of equation. Okay. Now, p, q, and r will automatically be assumed to satisfy this form just because we can. We're only considering like these special forms of equations to make our lives easier, or because they hold some special properties. Okay. Now, eigen somehow has made its way through literally every single field in existence. And yes, they do hold similar kinds of ideas, but basically we can create what we call eigenpairs. Now, eigenpairs are basically a collection of both an eigenfunction and an eigenvalue. So a linear operator has an eigenfunction phi if at all it's a solution for Lu equals lambda Ru, i.e. this form. And you can kind of see where exactly this comes from, because Lu essentially creates lambda times itself. So if at all phi solves that equation, then we get an eigenfunction, in a similar way to a vector being an eigenvector. If when you apply an operator, you end up with a parallel vector, or you end up with a vector in the same span. The eigenvalue lambda is basically just an extra constant, and this R will hold a special role later on, so we'll get to what exactly that is. But whenever it asks for an eigenpair, essentially what you're focusing on is a phi lambda pair. Alright, probably the most basic example of a Sturm-Liouville equation is the Legendre equation. I don't know how to say it properly, so hopefully that was okay. Okay, so let us suppose that we have the following equation: 1 minus x squared u double dash minus 2x u dash is plus this extra mu times mu plus 1 times u equals 0. Then what can happen is that we can condense this guy into the following expression, purely because negative 2x is already the derivative of 1 minus x squared. So in other words, we already have that idea that we have a2 plus a2 u double dash plus a2 dash u dash. So we can just kind of like use a reverse product rule so that we end up with 1 minus x squared u dash at the bottom, and then we have the extra dash on top. Now, in this scenario, we hold lambda r so that we get mu times mu plus 1 minus the 0. So in this case, the q will be 0. You can alternatively, like, I suppose that you can have like trivial eigenvalues, but like they're not as relevant nor useful, which is why we consider the mu times mu plus 1 as the lambda times r in this scenario, and the 0 as the value for q, just so that we can end up with some more interesting results. So now we can set p is equal to 1 minus x squared, q equals 0, r equals 1, with your eigenvalues of lambda equals mu times mu plus 1. But again, we can have something like, for example, eigenvalue of mu with r of x being mu plus 1. That is highly don't do that, because we want to keep the eigenvalues in terms of just a one expression, and we don't want it to appear anywhere else. So just make sure that we don't actually do that when we hit a question. Note that we need p of x to be equal to be greater than 0, and that's just a condition that we have to introduce. Don't need to know why, but that's just the way it is. Okay. So, a regular Sturm-Liouville eigenproblem basically considers problems of this form, which looks remarkably similar to what we had in terms of the Fredholm alternative from before, but essentially all we're doing is, instead of having f, we are considering lambda RU. With your boundary conditions being 0 to get your, I guess, regularity. So a regular Sturm-Liouville eigenproblem is something of this form, and these are all your extra conditions, which look like an absolute mess, but basically your coefficients can't sum to 0 in each boundary condition, and P doesn't vanish at the boundary. Those are basically your two conditions, and that kind of seems to, well, this part is kind of obvious because you don't want 0 coefficients at the boundaries, otherwise then you're not going to have nice solutions. And this guy just comes from just an extra assumption that we make, I suppose. There's no other way of really explaining these kinds of things apart from the fact that they're just there. You don't need to know why. From an exam perspective, probably not ideal. Okay, so let's suppose that we have the following Sturm-Liouville problem. So u double dash plus lambda u is equal to 0, where each one of your boundary conditions is 0. And all we're asked to find is the eigenpairs. So let's suppose whenever you're doing these kinds of questions, you only ever have pretty much 3 cases. The first case is when the eigenvalue is positive, the other one is eigenvalue is negative, and the other one is eigenvalue is 0. Deal with the 0 one first, get that out of the way. So if lambda is 0, then we're left with u double dash is equal to 0, so that we are left with our solution ax plus b. Now, since at 0 and 1, u is equal to 0, we know that our coefficients must be 0 themselves, which means that u is congruent to 0 over the entire interval. So we don't really care about that. That one's kind of like a useless solution. Now we suppose that lambda is equal to k squared, in other words it's positive, in which case we end up with our general solution as a sine kx plus b cos kx. Don't care what variable you use, as long as you use lambda as the eigenvalue, because that's what is defined here, and the fact that you use a squared term, because that one's always positive. Ultimately, because you're exhausting all cases, you'll end up covering everything. So even if k, sometimes k might not be an integer, as we'll see later on, but we can just assume that lambda will be a positive number. And in this scenario, what ends up happening is that we end up getting u equals a sine k pi x as the solution, and when we induce the initial conditions, we observe that k ends up equaling n times pi, and that's just because of when x is equal to 1, you end up with a sine, I guess k is equal to 0. So in other words, k has to be a multiple of pi, and an integer multiple of pi. So we have lambda is equal to n squared pi squared, with your eigenfunction being a sine n pi x. We don't really care about the a though, so we can just label our first eigenpair as sine n pi x, comma, n squared pi squared. And if we have lambda being a negative square, then we end up getting a u equals a cos kx plus b sine kx. Alternative way to view it is a e to the kx or a e to the negative kx, in which case you end up with u is equivalent to 0. So we only end up with one eigenpair, or one, I guess, collection of eigenpairs, which is sine n pi x times n squared, with your eigenvalue n squared pi squared. Alrighty, so So, when we have a regular Sturm Liouville eigenproblem, we end up with eigenvalues that are real. We don't really need to worry about complex eigenvalues because they're a mess. So when you're considering the regular one, you'll always have eigenvalues that are real. So the eigenfunctions from the regular Sturm-Liouville eigenproblem are orthogonal with respect to R, if and only if their eigenvalues are distinct. So again, similar to linear algebra, whenever you have eigenvectors and the notion of eigenvalues, whenever eigenvalues are distinct, the eigenvectors are going to be orthogonal to each other. And that's one of the processes behind spectral decomposition, but that's a story for linear algebra, not for Ds. But they both operate in similar wavelengths. Okay. So, we can consider this process of reordering just to make our lives easier, so that we consider a strictly increasing sequence of eigenvalues and their associated eigenfunctions, just to, I guess, make it easy to interpret. And what ends up happening is that the eigenvalues end up blowing off to infinity. In other words, lambda k approaches infinity as k approaches infinity. In the previous example, classic case, as n goes to infinity, n squared phi squared goes to infinity. Okay. Now, I show that the eigenfunctions from the previous example are orthogonal. So in the previous case, we had this problem. So it's kind of obvious that your eigenvalues go to infinity. In terms of your eigenfunctions being orthogonal, this is very similar to our Fourier idea, in which the integral of sine m pi x and sine m pi x, where you had r is equal to 1, because when we rearrange this guy, we end up with lambda r u. So your r will just be 1. So we have a weight 1, then we have sine m pi x, then sine m pi x, and then literally exactly the same way from what we've done before, we integrate it to arrive at 0. Alrighty. Okay, so this is just a formatting issue, so I will fix this slide up. I haven't had time to, but here's another example of a singular Sturm-Liouville. So here's an example of a singular Sturm-Liouville eigenproblem. It's where we have stuff associated with this, which looks very similar to the idea from the Bessel's equation with lambda equals 1. And what we can do is, if we suppose that u of x is bounded as x approaches 0, and x u dash is bounded as x approaches 0, with this extra, I guess, initial boundary value, then what ends up happening is, so that now we have two sets of boundary values. U of x is finite, and x u dash is also finite. As well as that x equals L, we have 0. Alright, so if we also have C0 times C1 is greater than or equal to 0, in other words, your coefficients themselves are either both positive or both negative, or both of them are 0, I suppose, then the eigenpairs will always take on this form, where kj is the jth positive solution to the following equation. And I guess one thing that you can remember this by is the fact that all you're really doing is solving Bessel's equation and then plugging it in to the boundary values. So Bessel's equation is the solution with lambda equals kj squared, has the solution of this form, where you have j v kj squared, sorry, jv kjx as your eigenfunction, and then with the associated value of lambda will be kj squared. And then if we plug in u is equal to jv kx at x equals L, we plug it into this equation and we end up with the following statement. So it's really no different to whatever we've just covered. All we've done is we've kind of automatically realized that lambda is going to take the form kj squared, or like some squared number, and then our solution will already take the form u is equal to a Bessel function with degree v. So we kind of just like already extrapolated the solution from our initial eigenproblem. Now, if at all, this extra line is basically, if at all we have mu is equal to 0, in other words, our solution is a Bessel equation of degree 0, then 1, 0 is an additional eigenpair, and that's just because we have if this guy is equal to 0, then what ends up happening is this guy ends up being non-zero. Sorry, this guy we can also have k equals 0 as your eigenvalue, and then associated with that is a constant, just so that you can get the extra eigenpair. Okay, so I guess the main takeaway from this is that whenever you come across a reformulation of Bessel's problem between two fixed points, in a way, like this first one is just basically defining some kind of fixed point. The point is that Bessel's equation can just be automatically used as a solution for this, where all you really have to do is recognize that lambda is going to be a square number so that we can get our nice solutions, and then we can just plug it into the other initial value problem so that we can get our extra condition on what the case actually should be. Now the Bessel function is basically looks something like a weird, I guess a really weird version of a sine wave, but essentially what happens is that you get a whole bunch of zeros in between for each selection of your kj. Sorry, for your Bessel function of degree v. And your kj's are meant to represent the x-intercepts for that Bessel function. So once we end up having that equation, once we end up having those values of kj, we can create our eigenpairs, and then from there we can work out what the overall solution should be as a superposition of all these solutions. So as a quick example, over here we have x squared u double dash plus x u dash plus lambda x squared minus 1 of u is equal to 0 over this interval, where u is bounded at 0 and u dash of 1 is equal to 0, which is very similar to what we already had over here. We don't really care about this guy at the moment. We can just get to that whenever we want. This will already take care of whatever we need to. The point is that all we need to do is really find the eigenpairs. And what ends up happening is, sorry about that, I misread the problem. U is bounded at 0, so that u is bounded at 0, and then our x u dash will be approaching 0 as x approaches 0 from the right, and this guy at x equals 1 is going to be this condition, so that we have c1 is equal to 1 and c0 is equal to 0. Now once we plug it in, we end up with C0 is equal to 0, so that essentially what we have is 0 over here, and then we have C1 times kj dash of KL, which is where we get this equation from. The C1 drops off because we don't really care about the constant, and that one is going to be undetermined, like an undetermined coefficient. All we really care about is what is the eigenpairs. In other words, what are the values of kj and what is the corresponding Bessel function associated with that value of kj. So kj will be the jth positive solution to that equation based on whatever we have over here. And then we find that our eigenpairs will just be j1 of kjx. Now the 1 appears because of the v squared over here, or the mu squared over here, in which case we have mu equals 1. Hence we have a Bessel function of degree 1 of kjx, along with the eigenvalue kj squared. Alrighty, so that basically completes the idea for generalized Fourier series. I guess the main takeaway from whatever we're seeing here is that you can express these different kinds of functions as combinations of these orthogonal functions, of these orthogonal sets, and basically come up with ways of constructing solutions in a really interesting way, I suppose. Other examples of orthogonal functions are the Legendre polynomials, your Chebyshev polynomials, and so on, and they all work in a very similar way to these, but a lot of the time they're not assessed because they're not as interesting as what you can get from the Bessel function and the Fourier and the normal Fourier series. So a lot of the questions are going to be primarily focused on those, but yes, the Chebyshev and the Legendre are two classic examples. Another one I think they covered in both 2121 and 2221 are the Hermite polynomials, which also have their own role in terms of Ds, but we won't really be covering those. Yeah, they're not really as exam relevant as one may think. However, yeah. Okay, so now for both 2121 and 2221, let us move on to initial boundary value problems in 2 dimensions. And this one is kind of like really out there. This is the one that most people struggle with, but thankfully, hopefully the lecturers are nice to us, and what a lot of these problems end up doing is they constantly keep doing the same thing over and over again, in that they solve PDEs using the exact same method that we're doing right now in terms of separation of variables. So essentially what happens is we take a function and we construct it in terms of 2 separate functions which are written in terms of 1 variable. So with partial differential equations, because we're going to be basing these off 2 variables, x and y, and writing our solutions in terms of these x and y functions, what we do is we assume that we can write them as capital X of x, and well, I've used the example of y, but again, similar kind of idea holds from before. We have y of y is equal to that other function. But the point is that we essentially assume that any function solution for a differential equation is going to be written of the form function of 1 variable times function of whatever the other variable is. In terms of 3-dimensional variable, in terms of 3D systems, they work in exactly the same way. You have function of 1 variable times function of another variable times function of another variable. And as long as you know what the Laplacian is for each one of those, you're not going to get higher order than a Laplacian. Like getting like derivative of derivative of derivative is virtually non-existent. So you can trust in the fact that we are only going to need this. essentially all we end up doing is we plug it into whatever the Laplacian is, and then rearrange the equation to obtain some kind of like new reformed equation that we can solve, that is solvable. So over here we have, let's suppose that we have x double dash, we have u of x comma t is equal to a product of x and a product times t. And all we end up doing is we plug it into the Laplacian, which is given by the second derivative of u with respect to x, plus the second derivative of u with respect to t. In other words, grad dot grad of u, which is equal to x double dash of t plus xt double dash. And that's just because x is not dependent on t, so it doesn't play any role in this, and apart from being times on its own, and x double dash of t coming from this term. Now what ends up happening is that we can rearrange. Now we'll just ignore this bit for now and just focus our attention over here. And when we rearrange this, we end up with x double dash over x is equal to negative t double dash over t. Now, what we do is we introduce this p-value, which is used to denote a separation constant. And the idea behind this guy is that all we're technically trying to do is find a basis of solutions. Ultimately, what we get through this value of p is that when we plug it in, we end up with a sequence of values for p after we plug in our initial conditions and all that, so that we end up with a situation similar to what we had from the Sturm-Liouville, the regular Sturm-Liouville problem, where we had the idea of an eigenvalue pair. We had the idea of an eigenpair. Okay. Now, once we create these bases of solutions, we can just essentially superimpose them and end up with our value. We can end up with a way to represent u in terms of these basis functions, because we know that we essentially assume that the basis functions form a complete set. So, basically, bottom line is separate u in terms of each of its components, plug it into the equation. Now, in the case of 2 dimensions, what ends up happening is we have only one separation constant because we only need to link the 2 variables. If we have 3 dimensions, then in that case we need 2 separation constants connecting 2 different variables. The other one automatically gets connected once we have an idea about what the 2 separation constants are. So we don't really need to worry about a 3rd separation constant. And for that same reason, because we're already connecting the 2 equations, we only really need 1 separation constant. So, once we assume the existence of a separation constant, we get x double dash minus px equals 0, and t double dash plus pt equals 0. Now, the interesting thing is that these two are really easily solvable. Depending on your values for p, given where once you're given your initial condition, you end up with ways to find out the values. We can find out what the value of x is given particular eigenvalues p. Given particular values for p, and similarly with your t component. But ultimately what happens is that because we are considering p to be equal in both these cases, we end up with a sequence of functions which can be used to represent u. So, literally all the problems are based on this same idea. Like, every time. So, thankfully, the range of questions that you can get in this regard is not really that many. Like, if you look back through the past few years of papers, you'll find that the same things over and over again. Okay. So, this is basically just a generic method for how to solve initial boundary value problems in 2 dimensions. You create a equation in which you separate each one of the variables, then you plug it into your partial differential equation that you have, and create these ODEs after using the separation constant. So once we have that, we solve for each one of our variables x and t, and then find a relationship between lambda and p. Like, we'll get to the lambda bit in a bit. But basically, you find your values for p, you create a connection between the two ODEs at the end of it, and then we superimpose the resulting solutions that we obtain from these ordinary differential equations. So it's literally just this method over and over again, though sometimes they can be with varying levels of difficulty. I know that in 2221, for example, they kind of throw in they combine the Sturm-Liouville form with this partial differential equation. In the context of 2121, it's not going to get harder than this, or it's very unlikely. So, a classic example of an initial boundary value problem in 2 dimensions is the heat equation, which I believe is relevant to both 2121 and 2221. Okay, so when we plug in, so we already know that we're dealing with u in terms of t and x. So what we essentially do is we assume that u is equal to a product of x and t. So now that we have that, all we do is plug it in, so that we get xt dash is equal to x double dash of t. And based on the initial conditions, we have u of 0 with respect to time. U of 0 comma t and u of 1 comma t is equal to 0 for each time coordinate. So all that means is that x of 0 has to equal x of 1, because when we plug in x equals 0 and x equals 1, we end up with 0. And that's regardless of what unit of time is picked. And since we already know that t of t, like capital T or small t, is not going to be 0, we can just directly assume that x of 0 and x of 1 are both equal to 0. Now, this one is not usable at the moment. That's just because we don't know what f of x is. And, sorry, not because we don't know what f of x is, because we don't know anything about the time component, apart from the fact that it's just when it's 0. So we don't have any actual information about how t behaves. Okay, so what we do now is we rearrange this so that we end up with nicer equations. So in this scenario, we have x double dash minus px is equal to 0, and t dash minus pt is equal to 0. Now, the reason for that is because x double dash over x is equal to t dash over t. So we've just rearranged, we've collected similar terms, and then we've equated them to a separation constant, p. So now we end up with 2 differential equations. Now, what we can do is we can take p or equals 0. We again solve it in a very similar to what we've described above. If p is 0, then we take our second derivative of x equal to 0 because of this equation. And so we find that x is identical to 0 after using the boundary conditions that we have over here. If p is equal to k squared, then similar case to what we had before, we end up with e to the kx, ae to the kx, plus be to the negative kx, and that yields x is trivially 0 again, because of the boundary conditions. And when p is equal to negative k squared, which is a really important case, we end up with x being a function of x is a sine n pi x, where p is given by negative n squared pi squared, which is this guy. So I guess one thing to note here is that while we didn't technically cover this in 2121, it is still handy to, I guess, understand what exactly is going on here, just because sometimes these can be really relevant. Okay, so now that we have information about how p behaves, which is a negative n squared pi squared, we can essentially just take this value and we can plug it in to pt, or t dash minus pt. So we have x, we now know what capital X is. Now our objective is to find out what we need to find out what capital T is. And now that we know the value of p, we just plug it in, and then we can solve for t in exactly the same way. So that we get t of t is given by an exponential. Now all this means is that any function of this form satisfied this equation. So now we know that we can essentially create un to be a solution of the form: this is your coefficient, this is your time component, and this is your x component. And the ultimate solution is just a linear combination of all these functions. So the tricky part will be to work out what an is, and this is where the other initial condition comes in. So we knew that when small t was 0, we had x of x times t of 0 is equal to f of x. So when we plug in 0, we end up with this as our function that we want, right? Because we got t is equal to 0. In other words, this guy just ends up being 1. Your an's are still kept, and your x's are still kept because, well, we haven't really plugged anything in for x. So now we know that u of x comma 0 is given by f of x, and then this becomes a normal Fourier series problem, where we can find an by using the integration formula. So a lot of the time your questions are just going to follow this exact same format over and over again, which is, I guess, kind of comforting in a way, because PDEs do tend to be a mess, and one can already see that given enough conditions, the solution can get messy enough. So it's really important to take care and make sure you don't get overwhelmed when doing these questions, despite how hard or weird they may seem. Because ultimately, they are fundamentally brought down to being the exact same thing over and over again. They're not going to ask harder than these kinds of things, because then it just gets messed up. Okay, now in polar coordinates, these work in very similar ways to what we've already described. So essentially what happens in polar coordinates is that you make a substitution: x equals r cos theta and y equals r sine theta, so that now the Laplacian can be expressed instead of partial of u with respect to x twice, the second derivative of u with respect to x twice, plus the second derivative of u with respect to y twice. It's instead expressed in this form. Now, it may seem really, really whack, or like really, really, I guess, out there when you first look at this, but at the end of the day, this is just there to help simplify the equation, and we can see how exactly that works when we approach a particular question. So let's suppose that we start off with this. Now, let's suppose that we want to solve for u when we're given that it follows the following conditions on a circular surface. So essentially we have something like a disk. So essentially at the radius, at the outer edge of the disk, we have u of 1 comma theta equals f of theta, and u is continuous everywhere, and the Laplacian is 0 everywhere in between. So there are two things that end up going on. Essentially, because theta can keep on rotating, we require some element of periodicity involved. In other words, u of r comma theta is u of r comma theta plus 2 pi, because we repeat it every 2 pi radians. So when we apply our separation of variables technique, we need to remember that there's one extra condition involved: the fact that h of theta equals h of theta plus 2 pi. In other words, it's periodic. The other condition is, well, we just plug it in to our differential equation. So the way this guy works is, when we plug in RH over here, we end up with 1 on r times partial r of r times r dash h. And then when we apply product rule over here, we end up with 1 over, what is it? R dash h plus 1 over r times r double dash h, or something like that. But basically, when you plug in the form RH into this equation, you can simplify it after multiplying by r squared to obtain this, which is a lot nicer. Then what ends up happening is that we rearrange it, and we rearrange it by realizing that there's a h here and another h here, so we can factorize, and then upon dividing, we get r squared r double dash plus r dash divided by r equals h, or negative h double dash over h. Yep. And then we can just include our separation constant equals p, and then we can rearrange to get h double dash plus ph equals 0, and we can rearrange to get that. So now we have two, I guess, differential equations that shouldn't be that hard to solve, given what we already know. So this one you guys should be able to recognize as Cauchy-Euler, and this one is just your standard differential equation. So given Cauchy-Euler, we can consider all our cases, and the only way that we can actually get the periodic case is, well, we won't really worry too much about this just now. We'll first solve our h component. So when we solve for our h, we can get, we have values for p equaling 0, value for p being positive, and value for p being negative. But we can also use the idea of periodicity. And okay, so if we suppose that p was equal to 0, for example, then we already know that your h has to be a constant, because its second derivative is 0. So if we impose the idea that it is periodic, that means it's a linear function that repeats itself. And the only way you can do that is if it's a constant. So we already know now that h of theta is equal to 0. Sorry, h of theta is equal to a constant if p is equal to 0. If p is less than 0, then we end up with h being in other words, p is equal to negative k squared. Then we get h equals a e to the k theta, a e to the k theta, plus b e to the negative k theta. Then, as a result of that, we get, as a result of it being periodic, we get a and b are both 0 because it needs to repeat itself, and the only way you can do that is if it's 0 in the first place, if a and b are both 0. So, now we have information, and then we have p is equal to k squared when it's positive, and that's when we get these trigonometric solutions. So now we know that p equals 0 and p equals k squared both generate possible solutions. We don't know definitely yet whether or not they are. By the way, I will release like fully worked solutions to these later on, so don't worry about skipping steps. They will be identified. So now we know the values for p. So, once we know the value for p, we obtain the following equation for r, because, well, if we know that p is equal to 0, for example, oh god, sorry about that. Okay, so now we know our values for p, and then based on that we can work out our values for we can work out the condition for r. So if we have p is equal to negative k squared, we end up with the following idea, that with the Cauchy-Euler case, we have what we suppose that r is equal to so capital R is equal to r to the power of lambda. We plug it in, so we get lambda times lambda minus 1 plus lambda minus k squared is equal to 0, and so lambda equals plus or minus k. Now, from the previous example, we could also condense p equals 0 into this case. So if k squared was equal to 0, what that essentially meant was that we would end up with a special case where we had a double root for lambda equals 0. So your solution is of the form constant plus b times log of r, with when k was equal to 0. And if k was not equal to 0, then your value for r is given by a r to the k plus b r to the negative k, as per normal, because those are two distinct solutions. Now, okay, so that's most of the hard part done. Now we have information for how r behaves, and we have information for how small r behaves. Now from that, we already know that r has to be bounded at 0, because this guy, continuous. Now we know that if we had r approaches 0, this guy becomes unbounded, which means that b has to be equal to 0 in the first place to negate any effect that it can have on the value for r, or on the value for capital R. So we now know that capital R has to be constant of a. So essentially, all that comes down to now, and similarly over here, this b also implies that it has to be 0, because as r approaches 0, this guy will approach infinity, or negative infinity. It will approach infinity, because r is positive. So now we know that r of small r is equal to ar to the k, where k is a natural number, because we have k equals 0, 1, 2, 3, so on to infinity. So overall, we now have we finally find the general solution for u. Now we have the existence of a constant, because of what goes on over here. Every 2 pi units, it must repeat. So we know that b has to have some kind of constant involved in it. Then we have r to the power of k from our solution over here for r of small r. And then your h of theta contributes this bit, which is over here. So this is our overall general solution given the separation of variables method. Now, from here, what ends up happening is we use the other condition that we have u of 1 comma theta is equal to f of theta. So, u of 1 comma theta has to be given by this expression, because we just plug in r equals 1, and f of theta is what happens as a result of this. And again, this becomes a standard Fourier problem, in which you take the integral to find each one of your b0s, ak's, and bk's. Of course, the formulas are kind of switched around because of the way we've defined coefficients, but the principle remains the same, that we take the integral of f along with the corresponding value that we seek, cos k theta, and then we can find our coefficients for ak and bk. Once we finish that, we have completed our solution for the problem. Okay, so that's pretty much all the hard part done. So that's pretty much how to solve it in the more common cases. It's very doubtful that you'll get three-dimensional cases because they take ages, and it's unrealistic to be able to do those kinds of problems. So you won't need to worry about like those. I suppose that you may or may not need to know the proofs for your spherical coordinates, Laplacian, and all that. But as such, you shouldn't necessarily expect to do separation of variables for spherical coordinates. But it's a good practice anyway to do it for the three-dimensional case. As far as I can tell, 2121 doesn't go past two dimensions, so you won't need to worry too much about that. But at the end of the day, they're all done in pretty much the same way, so you can take some comfort in that, I suppose. Okay, so the next bit is regarding the elliptic operators. So, with elliptic operators, what we essentially do is we can describe a linear operator in terms of its partial, like the partial derivative version, as a sum of all these second derivatives, a sum of all these first derivatives, and whatever the coefficient of u ends up being. So the extra important thing to remember being the fact that there's this extra negative sign at the front. So using this idea, we can define what it means for an operator to be elliptic. Now, essentially all this is that for every single value of x in a particular domain, if we can express a, we express a as a matrix of all these coefficients, where we'll get to an example of how exactly to construct these coefficients later. But basically we create these coefficients in terms of x. Then for each value of x in the domain, if for every y also in that same associated dimensional space, the degrees is given by the number of degrees. If we take the following inequality and prove that it is true, then we say that the linear partial differential operator is elliptic. The really important thing is the existence of c being positive, because if we set c equals 0, for example, then we can have some of these operators approaching 0, which is not exactly the point of what's going on. We'll get to what exactly that means in terms of the eigenvalues idea. We'll get to that. Okay, so first what we do is constructing, like once we finish constructing the matrix A depending on the coefficients, what we do is we take the symmetric part of A, which can be done using some linear algebra techniques. You have A can always be expressed as we got A is equal to, let's just say, what's a good one? M plus M transpose over 2. And yeah, so we first compute the symmetric part of A, and we find all the eigenvalues of that associated partial. We find all the eigenvalues of the symmetric part of A. Then we can create, then based on that, we can show that the operator is elliptic on the domain if and only if we can find, if and only if every single eigenvalue is always bounded below by a positive number. And we learned before, I guess, that we require the idea of positive. It's essentially analogous to the statement where we have positive definiteness, where where we require every single eigenvalue to be strictly positive in order to generate these elliptic operators. In other words, where we got this idea from. Again, it's not really the same, but it's a similar kind of idea to what we have over here from linear algebra. And we require that strict positiveness, and so that's why we need to include the extra c. You essentially also need to kind of verify that it's not just going to be strictly positive for all values of x, because sometimes it can approach 0 along the boundary, which isn't going to satisfy the definition that we need, because it needs to work for everything that we are considering. So we need there to be some kind of like a lower bound on lambda for each value of x in the domain. Okay, so how exactly do we construct the matrix? Essentially, we first construct the matrix A, which is going to be given by 2x plus 4 partial 1 squared. So that's where we put the 2x plus 4. Then we have 2x plus 1 partial 2 squared, so that's where we put the 2x plus 1. So whenever we're considering the second, so this matrix A is purely determined by the second derivatives. So, if at all you want to not get confused, you can factorize out the negative and put brackets around it. So you got negative 2x plus 4, which is where this goes. Then you have 2x plus 1, because we've factored out the negative to go over here. And then we have negative 3, because we've factored out the minus sign, we have a negative 3 over here. And then over here we have negative 1, so that we have negative 1 over here. Now, the ordering is specific to what exactly you use as partial 1, partial 2. So because this is referring to, I guess, row 2, column 1, we're first multiplying the partial 2 operator. Sorry, we're first doing the partial 1 operator and then the partial 2 operator. So it goes in row 2, column 1. In a similar way, we have partial 2 first and then partial 1. So we put this in row 1, column 2. Or column 2, row 1, however you want to say it. The symmetric part will be given by this. So I suppose the diagonal elements will be the same, and then you just have to work out the other two terms so that we get a symmetric matrix. So it's just going to be the average of the two terms. So you get negative 2, negative 2. The eigenvalues of this matrix, which is you just use some linear algebra stuff, by using the determinant ideal, you can solve for the eigenvalues and get 2x and 2x plus 5. Now, this interval that we're considering is 0 to 1. So our eigenvalues are 2x and 2x plus 5, but what you can observe is that as x approaches 0, 2x approaches 0. So in other words, we can't find a positive lower bound for your eigenvalue, and so the operator is not elliptic. However, if we, as mentioned here, if we consider some kind of like positive number, if we kind of just put, let's say, 0.01 to 1 as an open interval or closed interval, however you want to do it, then what you can show is that x approaches 0.01, 2 approaches 0.02. So you can find a constant c equals 0.02 so that the equation is satisfied, so that this idea about the eigenvalues being bounded below by a positive number is satisfied, and so that verifies the condition that the operator is elliptic. Okay. Elliptic eigenproblems, you don't need to know the theory for it. They're way too insane, so we won't really need to worry about it too much. But whenever we are considering these kinds of problems, this again is only for, now we move on to the stuff that is purely just for 2221. 2121 can do it for extra understanding if they so desire. You don't really need to worry about why exactly it works, nor why. You don't really need to know about why it works. Just the fact that it works is enough for 2221. There is a whole bunch of theory about it, which we did leave out after doing this example, mainly regarding like the green identities, Steklov eigenproblems. Those kinds of stuff are just like very unlikely to be assessed given the time frame required for differential equations exams, and the fact that PDEs generally tends to be enough. But all we do is we just keep on borrowing these ideas over and over again from previous, I guess, examples that we've done, and we just keep on doing those and applying it to all these kinds of new problems. Okay, so we begin by, apologies if this goes over time, let's suppose that we wanted to find the eigenpairs of the system. Constructing the solutions thereafter isn't actually all that difficult after you plug in the initial conditions and basically reuse the same method that we did from before. To find the eigenpairs of the system, we first set up, we're considering the unit square. So we first set up the separation of variables idea, so that u is equal to x of x times y of y. Then what ends up happening is we rearrange it so that we get x double dash y plus y double dash x plus lambda xy is equal to 0. Now, when you finish rearranging it, you'll end up with x double dash, what else can we do? Oh yeah, so we got x double dash y plus y double dash x is equal to lambda xy. Then dividing both sides by xy, we end up with x double dash over x plus y double dash over y is equal to negative lambda. Then we can bring one of the values to the other side so that we can get something really nice. X double dash over x is equal to y double dash over y minus lambda. So now our right hand side becomes one function in terms of y, your left hand side becomes one function in terms of x. Wait, I missed a negative sign, didn't I? Yeah. So as long as you remember that there's a negative sign on some place, so negative x double dash over x is equal to y double dash over y minus lambda. Then we can introduce our idea for the separation constant, so that's where the extra p comes from. And then after rearranging that equation, we get this on our left hand side and this on our right hand side. Okay, then we plug in our initial conditions. So we have u of x comma 0 equals u of x comma 1, which is also equal to 0. So all that means is that y of 0 equals y of 1 equals 0. And that's just because when we plug it in, we get x of x times y of 0 equals x of x times y of 1. And this works regardless of the value for x. So we have the initial conditions for y, or like the boundary conditions for y. Then we also have our boundary conditions for x using the second set of equations, or third set of equations. In a similar way to what we've done before, we can find our eigenvalues for x because it's super easy. And we can see that using the initial conditions of these, we get p is equal to m squared pi squared, because it only works when p is positive. When p is 0, we just end up with a trivial solution given by this, because of the nature of the boundary conditions. And for the negative case, we just end up with the exponential solutions. Use Kosh or Shine either way. Yarn won't care. So, we get x double dash plus k squared x equals 0. And so we are left with our eigenvalues as m squared pi squared. So your eigenpairs associated with x are going to be m squared pi squared and cos m pi x. Now, once we know the value for p, we can then work out the value for lambda, but we won't really worry about that right now. What we'll mainly focus on is just working out what is the new eigenvalue. So now that we know what p is, we move on to just simplifying lambda minus p as mu. Point is that all we're doing is we're finding the eigenvalue, well, we're finding the cases or solutions for y in terms of this new value. So let's suppose that we have mu is equal to 0 in a similar way to what we had before. You'll just get y congruent, y is equivalent to 0. If mu is positive, then we end up with y is a sine function with mu equal n squared pi squared. Now it's really important that you use different variables because mu and p are related, but they take on different values. They could take on different values. So if at all you don't use a consistent naming scheme, as in if you repeat the variables, then you'll easily get confused. The values for p have already been determined, but mu still hasn't, so you can't use m. So we now know that mu is n squared pi. And if mu is negative k squared, then we just end up with a trivial solution. So now we know that mu is n squared pi. We know that p is m squared pi. So what ends up happening is that we now know mu, p, now we can work out lambda. And the ultimate point of the question was to work out the pairs lambda and u. So we know that lambda m comma n is equal to mu plus p, which is given by this, which is why we can't use the same naming scheme, because our objective is to work out lambda, which is dependent on two separate eigenvalues, which are related in a way. And then our corresponding eigenfunctions will be a product of whatever the functions were based on our x's and y's. And then superimposing them will get us our general solution. Okay, so that completes the seminar. Some useful, I guess some tips and tricks for the final exam is that you will be doing a lot of working out. So make sure you don't lose track of what exactly you're doing. And because it's really easy to make simple mistakes, especially in something that is 2121 and 2221, where it is a very memory-based subject. Like if you don't remember the method, you can't do the question. I suppose that can be said with anything, but particularly with 2121 and 2221. Just make sure that you are able to remember all the different kinds of methods that are used, and also remember that I guess if you don't keep the question simple, it will be difficult to do the question. Like ultimately, every question will be doable in the exam. I'm not sure how Anna has framed her questions, but I know that with Jan, he gives not necessarily easy questions, but questions that can be easily done, even if they require a lot of work. So don't be surprised whenever you're doing questions, whether or not they do take a long time. If you keep pushing through the question, you will get the answer. And yeah, I suppose that's probably just the main trick involved in 2221 and 2121, is that make sure you remember all the methods and you do literally every single question from the past papers, because ultimately they're not going to divert too much away from that, or they shouldn't be diverting too much away from that. So yeah, I suppose that concludes it for the revision seminar. Hopefully that helped you guys. So yeah, good luck for your exams.